better, but in the extremes case where it's only like 7 ratings for each user, we can't see a lot of difference. And this is the prediction time. So our method performs far much better than the method the other proposed. And this is for the number of known ratings.
Okay, so now I will draw the conclusion. And so in this work, we propose a user matching pursuit methods, which use the assumption that a user behavior can be decomposed into some basis behavior. And empirically, the experience result shows that our methods can make competitive and fast predictions. Thanks.
So how does this relate to PCA? Because one of the baselines is simply PCA, right? That you get a new point and you just project it to the subspace. And in your method, you seem to be linearly combining it based on some neighbors and then projecting it.
So what really do you refer to that is related to PCA?
The one of the baselines that you presented, the first one.
This one?
Yeah, this one. No, this is your method. Right?
No. This is related work.
Oh, sorry.
Yeah, and
this is another related work.
I guess my question is just that, is this in any way related to principal components analysis? Because the basic problem is, right, it's just PCA, the matrix factorization one, the top K.
So you mean this problem is somehow like a PCA problem, or?
Isn't it?
But I think the R is only partially absurd, so this is not entirely
we only have some interest in R, and also when a new user comes in, we add there's a new role in rating matrix and a new role in user matrix. Yeah.
So the observed matrix R is not like it's not a truly matrix. It's only a partially interest of that matrix is observed, and the rest is all unknown.
Yeah.
So we cannot directly use PCA to factorize the R.
How does this compare to the standard sparse coding methods that are used for matrix computation or the objective function of your method?
Yeah, actually, it's similar to sparse encoding, and actually we done a experiment that just try to learn a dictionary on P, and so we can obtain some basis from by this method. But the result shows that the performance is very poor, and I suspect that it's because that we did not engineer that the similar users should have similar user vector in the original matrix factorization problem. So even if the ratings between two users are similar, but it turns out that the user vector can be very different. Yeah.
So we don't have more time for more questions, so you can discuss that.
Okay.
So let's collect these forms and then think for computer
Is this cool?
Is there some problem with that?
Does that not work?
We tried with that.
Try it now because it wasn't.
Can I change these two? How can I change these two? This is great.
Ready?
Yeah.
So you have 10 minutes.
Yeah, sure. Hey, so we are interested in the problem of incorporating side information in tensor completion. So why tensor completion and what is side information? I'll go through the, yeah. So we are aware of the matrix completion problem and how it's useful for the recommender systems problem. And a similar problem is that of image restoration. So here you have rows of pixels, rows and columns of pixels. And the traditional way of solving this would be to approach this as a matrix factorization, where you associate each row and each column with a feature. And the pixel value at a specific cell is basically the inner product of the row feature and the column feature. But then at times you might have